There you go. That's one way to tell. Well, I'll see you Wednesday.
I see you.
Oh, there's something I was going to ask.
Mhm.
I am looking to go down to the Rio Grande Valley. They have a college down there that has, I've told you about this before. They have a tuition waiver program for low income students. So I would be able to go to college for free if I keep my grades up.
Mhm.
And I was considering their civil engineering program or their chem. I know you had some experience doing like upper level OChem. I kind of wondered
Yeah.
what made you drop it.
Organic chemistry was just
Nightmare.
it's one of those classes, like there's certain classes, like you were saying earlier, that are meant to like be the cutoff point of who we keep and who we let go.
Yeah.
And that's one of those classes. So sometimes it's abnormally hard. It's already hard, but sometimes they make it abnormally hard. It's sort of like a cutting off point to get rid of certain people. In that case, it would make sense because a lot of those people would be doctors.
Yeah, fair enough.
So we're like sort of weeding out the people who probably should be doctors. Like college algebra is supposed to be one of those weeding out courses. So if you find that you like don't have the time or something happens to your schedule, it could be a really hard class to pass. My thing was like, I got to it and I had realized I had tons of math credits. So chemistry is my thing. I think I want to be a mathematician.
Yeah.
But it's really, that's the class that throws everybody off, is that organic chemistry. Yeah. It makes everyone cry. Doesn't matter who you are, you cry.
Is that like a second year class? Like, I know
You do basic chemistry for 2 semesters. So yeah, I think it would be a second year class.
Yeah. Great. Wonderful. Yeah, my mother did biology. She got all the way through her master's in marine parasitology, which is a weird specialty.
Yeah.
I didn't even know Tarleton like did a master's in marine parasitology, but apparently they do.
Huh.
And, she was talking about doing some research where she was at, and there's just some really neat chemistry research going on right now,
Yeah.
especially around energy production and water purification. I was thinking,
All right, thank you for connecting me. This was supposed to do it on its own, but for some reason it didn't. Oh. All right, I'll give it a few seconds because we're missing quite a few people. I don't know if you wanted this ahead of time.
No.
I said I didn't know if you wanted this ahead of time. You were here last time. Okay. I was gonna say, this is the one for chapter 2. Might not get to it. Okay, so those of you who are in Ranger, if you needed handouts, if you look in the front of the class, there's this podium that's sitting up there to the left. They should be sitting on that. But there should be one for chapter 2 and then one for chapter 1, and then there's 2 different ones for chapter 2, I believe. Actually, hold on. Yeah, I think I got this on order. I think if we do the second half of the chapter. So then if you can't be here next time, you have them. So for those of you, if you can't make it in to pick up the handouts, that's fine. If you look in your class content, so you look over chapter 1, you'll see notes. So we're just covering these notes in here. It's just so the packets I handed out is where I put all those sections all together. We're doing chapter 1 still. I just figured you might as well grab chapter 2 while you're at it in case you, when you have it. Yeah, so if you were in Ranger, I handed out chapter 1 last time. There's some chapter 1s left up in front, and then there's 2 parts for chapter 2. If you need to grab those, if you want to grab them ahead of time. All right, exactly where I was now. Okay, so what we had done last time is we were talking about a little bit about functions and linear equations and all this stuff. We were working through that. It was basically a review. I'll get attendance towards the end. Maybe more people will show up by then. We have a lot of people missing this week. I don't know what's going on. Yeah, I don't know. Yeah, and then you guys in Ranger, if you need me to hear you, you have to go up to that thing in the front, and there's a microphone. You have to unmute it. Because I guarantee I will not be able to hear you right now. Ranger, Texas, main campus. I have it set up to turn everybody off when they first join in, because when they join in from their dorms, they forget to turn it off. All right, you guys can hear me then. I can hear moving, so at least I can hear you. All right, I think we did this problem last. So we did find the intercepts of the equation?
Yes. Yeah, that's,
Yep. So we were here on the symmetry. So let me go up and just show you something here to explain the symmetry part. So I'm going to pick a point. We'll have a point here at 3, 4. And we know that this is my x-axis. So if I were to reflect this point over 3, 4, yeah, sorry, I can't get that to connect. It's been happening all day at this point. I finally just gave up. If you reflect it over the x-axis, it goes from 3, 4, and it goes down here to 3, -4. So what you have here is it's your y component changes from a positive to a negative. Now, if I take that point and I reflect it over the y-axis, and I reflected it too far, there we go. It goes here. Now this point is -3, 4. So in this case here, the only thing that changed between those 2 points is that your x component changed from a positive to a negative. If I reflect it twice, so I reflect over x and then y, or y and then x, it's got 2 reflections here. This point is -3, -4, so it's both the x and the y component that changed their sign. So the way we're going to talk about looking at symmetry is looking at the ordered pairs and seeing if you change it from an x to a y or both, or sorry, if you change it from positive to a negative, either the x or the y or both, if it's going to be the same equation or not. What we have here is that if an equation was symmetric this way across the x-axis, this point we know reflects here. We know it's just that y component that changes. I put this all on one screen. It's almost impossible. Here, if I reflect across the y-axis, this point here reflects over here, and it's just that y component that changed. So we're talking about the symmetry, we're talking about we reflect that graph, it's symmetric across. If we have this kind of symmetry, it's called symmetric about the origin. It means that this point and this point are the same, except that both change from a positive to a negative or negative to a positive. Right. So a lot of stuff goes quickly because it's supposed to be review. And what we're trying to do is use a little bit more of the math notation that you'd see if you went on into calculus. So what we have here is that we can say a graph is symmetric with respect to the x-axis if for every point xy, we could graph a point x -y. I'm gonna draw a little picture next to it so you know what we're talking about. So we're talking about something that looks like this. All the x values are the same, but on the top part, they're all negative y, positive y values, and the bottom are all negative y values. For symmetric with respect to the y-axis, this is what we call an even function, if you remember. Then what we have here is that my y values are all staying above the x-axis here, but it's my x values that are changing from positives to negatives. And then when we're symmetric about the origin, that means we have graphs that look like this. So what it is, if you took that graph and you like sort of flipped it around halfway, so 180 degrees, you get the same graph back again. So this point here, it's a positive pair, goes down here and it becomes a negative pair. So symmetric to respect to the origin means we take every pair x, y, then there should be a pair negative x, negative y that's also on the graph. And this means that we did two reflections. Means we're symmetric about the x-axis and the y-axis at the same time. I think that's about what we had last time was 5. Okay. So these are graphs showing you the same thing again. Let me make them a little bigger so you can see. So that's symmetric about the x-axis. So you see we have these points here, x1, y1. That means that if it's going to be symmetric with respect to the x-axis, there has to exist a point x1 negative y1. So what we're saying is that those 2 points have to exist simultaneously. If we're symmetric around the x-axis, and I have a point negative x1, y1, then there has to exist a point positive x1, y1. Like I was saying, the symmetry means those 2 points have to exist simultaneously. Let's move this over so we can see. And then this one with respect to the origin, kind of like this point. We took it, it reflected here, then it reflects over here. Sorry, it's not to scale exactly. But if I have a point that is, sorry, x2, y2, then there has to exist a point negative x2, negative y2. You guys have any questions so far? So we'll work on this one here. So we have this equation, x squared minus 9 over x squared plus 2. We want to find the intercepts and test for symmetry. So like I said, this is kind of just a quick reminder of how to do this. If I want my x-intercepts, that's when y equals 0. That means I have to have my x squared minus 9, x squared plus 2 has to equal 0. We'll do this part first. So I'm going to blank out this part underneath for right now. So like I said, I think everybody in here has had college algebra or some pre-cal. Now, if you have a rational function like this and you want to figure out where it equals 0, just recall it's the top part we have to set equal to 0, because wherever the bottom is equal to 0 is where it's undefined. Oh, just trying to figure out where that voice is coming from. So my x-intercepts are plus and minus square root of 3. Or square root of 3. It'd be 3, not square root of 3. So the voice distracted me. If you want to find y-intercepts, that's where x equals 0. This one's always the easier one to find. Because now I have 0 squared minus 9, 0 squared plus 2. So I have negative 9 over 2, or negative 4.5. So now we got those ones out of the way. We can do this next part. This is all going to be algebra. I'm going to, oops, need that to be, wait, because the red is a little too much. More space here. So when you're testing for symmetry, and we'll look at Desmos graphs here in a minute and see how it looks. So we said that our function was y equals x squared minus 9, x squared plus 2. So if we want to test for symmetry about the x-axis, what was the one point that changed when we were looking at ordered pairs? We'd had x-y pair. If I reflected across the x-axis, the y changed. So we replace our y with a negative y. So we know this is the original equation. So now I'm going to take it and I'm going to replace that y with a negative y. And then I'm going to solve for y. So when I do that, that just means I move the negative over on this side. Now I get negative x squared minus 9 over x squared plus 2. And what's important here is that this is not equal to my original equation. So when I replace that y, when I replace y with negative y, we get a different equation. So the function is not symmetric, or this, whatever's going on here. Let's say the graph will not be symmetric. Trying to put this in here. So it should not be symmetric about the x-axis. If there's something in the screen in the way for you, those of you on the main campus, let me know because I can't see your screen and I know weird things pop up on that one. I'll do this next part in green. So when we were testing to see for symmetry around the y-axis, then it was x that changed. That was a little easier. We're going to place all our x's with x squared. So now we keep that y, but now we have negative x. Sorry, I think I said replace all our x's with negative x. I was thinking I had x squared. So instead of having x squared, we have negative x squared. So what happens when you square a negative? What happens to the negative? The negative disappears. So I'm just really left with x squared minus 9 and x squared plus 9. Or plus 2, sorry, got the wrong number. So I have the same equation. So the graph is symmetric. So you typically, if you're symmetric with the, as far as functions go, with the y-axis, then you're not going to be symmetric with the origin. We're going to test it anyway. So with the origin, and let me know if the color doesn't show up, we were going to replace our x with negative x and our y with negative y. So we have to replace both of them. I was trying to make it a little simpler there. So I'm going to cooperate. So now I write negative y, negative x squared minus 9, negative x squared plus 2. So we try to solve it for y again. So we get negative y plus x squared minus 9, because those x negative squares become positive squares. And then if I move that negative over again, I end up with a negative x squared minus 9, x squared plus 9. So this one's not symmetric about the origin. About the x-axis. Oh, that's Now let's go back to that for a second. I think somebody just walked in. Where did it go? There we go. So is that Priya that just came in?
Yes.
Just to let you know, in case like you can't make it next time or something, if you look on that podium in the front, there is the handout I gave you last time for chapter 1, but then there's also 2 parts for chapter 2. So if you just want to take them like now or leave them for later, it's up to you.
Okay.
At this point, I'm just prepared for people to be out sick. I'll give you a second to fill that in, that last part anyway. Trying to look up your attendance, but it won't come up. We need our Desmos graphing calculator.
I'll get it out. Probably need a number. Have you like send me pictures or something?
So y was x squared minus 9. Sorry, if you're still writing something and I can barely see you guys, just let me know. X squared plus 2. Again, we did find what we thought we saw. If you look at this thing, the only place it's reflecting is across the y-axis. I could fold that thing in half and I get the same picture on both sides. Okay. Guys have any questions? This next part is, like I say, it's really heavy on review, so we might kind of hop over a few things here. This is really just linear equations. Sorry, I think there was one problem I missed there. Oh, I see, I messed up on my notes. So we want to graph the equation of y equals the cube root of x by doing the following. We want to find the intercepts, test for any symmetry, and plot the points. So what we're trying to do is use symmetry to make this go a little faster. So if I want my x-intercept, that means I set y to 0. So what is the only thing that x can be where if I take a cube root of it, it's going to be 0?
0.
0. Or you could just cube to both sides, I guess, as well. But in the end, what you're getting is x can only be 0. That means we have a point at 0, 0. If I do my y-intercept, then that means I have to have my x is 0, so I have y equals cube root of 0, which leaves me with y equals 0. So the only place we intercept is the origin. So frequently, if I'm intercepting the origin, that's a good hint that you probably, when you're looking at symmetry, you might want to consider looking at it being symmetric about the x and y axis. If you do this, if we replace, I'm going to have to erase some of this, x with negative x, then we get y is equal to the cube root of negative x. So let's see if you guys remember this. We talked about in the past that if you had a even root, then that meant you can only have positive values inside the root. Now, if you have odd roots, can I do odd roots of negative numbers? Does anybody know what happens to that negative? No, not when it's a odd root. In this case, I can do this if you wanted to. But what's important is it's still not this. So it's not symmetric with the y-axis. So I'll get rid of this part over here. And we'll do the other symmetries. I'll replace y with negative y. So if I do that, well, that gives me y is equal to negative 3 over x, which is still not equal to, sorry, yeah, I got that right, which is still not equal to the cube root of x. So it's not a symmetric about x or y, sorry, y or x, so that backwards. So if you want to test y, you change x. If you want to test y, you change, sorry, if you want to test y, you change x. If you want to test x, you change y. Been seeing this like stuff all day. It's starting to mess with my brain. So now we replace x with negative x and y with negative y. So this tests the origin. All right. So I can bring that negative over here from the y. And then I had said before that if I do a odd root, so like a cube root, a seventh root, something like that, and there's a negative, I can pull that negative outside of the root. Finally, we got something we like. We got the same graph back. Should I spell symmetric again, correctly again? Symmetric about origin. So how we use this for graphing? Well, we know that y is the cube root of 9. Cube root of 9, sorry, I got ahead of myself. Cube root of x. So if x is 9, what's the cube root of 9? Oh, 29. Let's try this again. Let's do 27. That'll make more sense. Does anybody know what that one is? No, what if I did 8, which is what I wanted to do originally when I said 9? 2. It's a little easier to see. If I did a root of 1, I'd have, and then we have 0, 0. Okay. This is where that symmetry comes in. So symmetric bound the origin meant if I had a pair of x, they're xy and they're both positive, the next pair would be xy components are what? Negative. So we have a point -1, -1, -8, -2, and a point -27 and -3. Yeah, I think you guys just like did within a day and a half what's usually like 2 weeks of college algebra. Any questions? So our next section is 1.3. So this is just doing linear lines. And then I think our last one's circles. No perpendicular lines, circles is later. No, I was right, it is circles. So this one I'm probably going to push a little faster through because I know most people have done linear equations a bazillion times by now. Circles are a little different. Like this. When you walk upstairs, there is certain steepness to them. The steepness can be calculated using the term slope. Slope is a numerical measurement of the steepness of a line and can be found by the following. So this is more of your terminology that you would see if you were taking higher level math classes. So we're going to have P and Q are points. Like I said, this class is preparing for calculus. And when we talk about, believe it or not, slope in calculus, we're talking about it being between these points P and Q. These are 2 distinct points. So we have x1, y1, x2, y2. So college algebra, I think we just had the x's and the y's, but we didn't have the P and the Q. So to have a slope, it's important that your 2 x values do not equal. Because if you don't, then we have an undefined slope. I'll write this here. So remember, undefined. An undefined slope doesn't mean it doesn't exist. It means I just don't know how to talk about it. So the slope M of a non-vertical line containing the points P and Q is defined by the formula. Does anybody remember? y2 minus y1, x2 minus x1. All right, so I just have to ask, do I have to put the y2 and x2 first? Does it actually matter? No. So when you get down here, if x1, y1 are not equal, then L, so L means line. So it's the name of the line. L is a vertical line and has a slope that is undefined. So the other ways of defining slope is we talk about a change in y over a change in x. We use this delta. Oops. Stop wiggling and do change. There we go. This is delta, so it means change. And I just caught on that when people are talking about delta V, they're talking about a change in velocity. But that's where it comes from because that means change. And so, like I said, you have y1, y2, you can actually just have it, sorry, y2, y1, you can do y1, y2. The point that's always important here is that the points that go together are stacked on each other. So x2 goes to x, well, to y2, so those go together. You put the y on top of the x. All right, so like this part here, real quickly. I know you can pretty much know this. Consider the line below from the bold line, bold the line. So we're talking about this one. It's not catching me here. There we go. A line drawn vertically up to each line. So if I drew a line like this, and then I'm gonna straight and use blue for the other one. And like I said, from the bold horizontal line, we're going to draw a line up to each of the lines. This demonstrates the same run. So this is your run down here. I put a little difference in there just so you can see them, but you're thinking they're hitting in the same place. So we have the same run, but we have different rises. So we're going to call this A and they call this B. So the steeper the line, what would you say, what happens to the slope? Okay, what? Greater the slope? Okay. Oh, I didn't hear you, sorry. I thought maybe I heard it and then I heard you saying something else. I didn't hear it. So just like quick practice here. Now, if I give you, find and interpret the slope of the line that passes through the points 1, 2, and 3, 6. And then once again, doesn't matter which you use first, which one's P and which one's Q. This part here, I can answer it very easily for you. No. You just decide which one's P and which one's Q. I can make this one P and I can make this one Q, or I can switch it. It's not going to make a difference. All right. So the way I usually think about this, like I said, doesn't make a difference, is that we know these are X and Y pairs. So just make sure that you put the Y on top and the X on the bottom. And then next same thing, the next point, you put the Y on top and you put the X on the bottom. And then just remember you're subtracting. And just to demonstrate, if I flipped it and I did it the other way, Come on, catch the right note there. So if I switch my points, it would look like this. That doesn't matter because what I end up here is -4 over -2, which negatives cancel. I'm left with 2. If I use this Q first as my point, then I end up with a +4 over a +2, and I end up with 2. So as long as you keep your ordered pair together and stack them, then you shouldn't have any trouble. Sorry, I had a message coming up with seeing if it's something problem we were having, but I think we're okay. Let me go back and look at this problem. Okay. So here we want to, right, second, I'm giving the internet a second here. That it was unstable. Just to point out, all of these have the same starting point. It's just the Q is different. So if we're going to graph these, all we need is a point and we need a slope. So we already know where one point is going to be. They all are going to be through, yep, 2, -1. So just practice with your slopes here. So if I'm going to do my slope of this line, what do you want to do? P first or Q first? Do Q first? All right, so do I put 4 over 3? Oh. Yeah. So if I put this pair first, what's the number I put on top? The 3, then the 4. And then same thing here. Put the -1 first, then I put the 2. So always remember you're subtracting the second pair of points. So here I end up with a 3 plus 2, so it's a 4 over, sorry, 3 plus 1, so that's a 4, and then you get 2 at the bottom, so we get 2 altogether. So if you're trying to think how to graph this, essentially you have 2 over 1. This is a change in your y's, and this is a change in your x. So x goes over 1 and y goes up 2. All right, does everybody remember doing that before? I'll do the other ones here quickly for us. So if we do the next set of points, you're going to end up with a 5 over -3. So when you have the negatives, I always say you think of the negative as being attached to the y, just to make it a little easier. So your x goes over 3, 1, 2, 3. And then because of the negative, that means the y goes down 5. I'm trying to make sure I get it in there correctly. So we get this point here. Because these have names, this is line 2, so we put L sub 2. This was, purple one was 1, so it's L sub 1. So I just want to point this out here. So typically what's got in here, it's got L2, L1. We actually write that, and we just subscript that 1. So instead of writing it right next to it, make it a subscript so we know it's not multiplication. Let's do blue for the next one. So I'm going to have 5 divided by 2 minus 1 divided by 2. So what happens with this one? It's 0 on the bottom. Do we like zeros on the bottom? This means we are our slope is undefined. So see if anybody remembers, when your slope is undefined, do I have a vertical line or do I have a horizontal line? Is what? Vertical. Because if you notice, I have a y here, and then the y values are staying the same. It's just the x values are changing. If I put those two pairs down. So essentially we have an undefined slope because I have no way to define that steepness. I don't know what value to apply to it. It's infinite steepness, I guess. And then my last one is going to be a 0 again. So we have -1/8, -1/2. So we're going to have 0/6. Slope is 0. So if my slope is 0, that means I don't rise up and down at all. This was L4. Let me label this one. This was L3. I meant to move something, not clear everything. This section's going to take me a little longer than I thought. All right, so going back over what we just did. So when our slope is positive, our line slants up or down. So going left to right. So if we got a positive slope, left to right, we look like that. So it's going up. If left to right looks like that, then that's down. So remember, anytime you're looking at anything to do with graphs, you're always starting from the left and you're going across, going to the right. When the slope of your line is 0, then our line was horizontal or vertical. Horizontal is basically there's no change, so it stays flat. And then when it's undefined, then it has to be vertical. So essentially what's happening at that point is it's so steep that it's like infinitely steep and I don't know what to say about it. It's undefinable. I keep having to check the time when we get out because it's because Tuesdays and Thursdays I start earlier, but I get done later. So I'm sitting there going like, wait, what is it? Yeah. Okay, so my graph line's given a point. I guess we already did this. Here, let's just quickly. So we're given the point -1, 2. So if I have a slope of 2, because I always think of these as like 2/1. So it's always y over x. My x moves over 1, my y moves up 2. All right, was that a sneeze or?
Yeah.
Oh, okay, bless you. This one here, you always think of the negative belonging to the y. So we still got that same point. It's just now we're going to move forward with the x. So it goes 1, 2, 3. But then that negative, like I said, you think it going to the y, so we go down. Okay. How do you guys feel about vertical and horizontal lines? Because I'm thinking here, I might kind of skip this part. And once you do these ordered pairs, but we know that if x is -4, I have to cross through the x. That means only a horizontal line will work. So we'll cut out a bunch of this, or sorry, vertical line will work. If y is 2, then that means that I have to cross that point, because that's where y would be equal to 2. I get a horizontal line. I was hoping to put that bottom part in here at the same time, but I think I have to wait. Never heard of there being an equation for a vertical line theorem, but apparently it's a theorem now. A vertical line is given by an equation of the form x, we say a. So usually when we're talking about x values, we use a. And we're going to say a is the x-intercept. When we talk about y-intercepts or y values, then we usually say it's equal to b. So you're thinking of a and b as a real number. This is one of those things that's not like set in stone. It's just typically when we talk about x's, we use an a. When we talk about y's, we use a b. And then at some point we change our mind. So this part, I think most people have seen this. There are 2 equations that we typically, there's 3 of them, but 2 of them we use the most when we're talking about linear equations. So this one's going to be your point slope form. So essentially what this is saying is that these are going to be a variable. So x and y, but this x1, y1, these are a known point. So what we're saying is that I have a line where I have a known point and an unknown point, and I want to write an equation for it. So if I talk about my slope, so I'm writing this part out here, then I just put my y minus y1 over x minus x1. Now, if I multiply both sides by the x minus 1, I end up with m equals x minus x1 equals y minus y1. As I say, a lot of you had in college algebra, we use this formula a bazillion times. So like I said here too, clear the fraction by multiplying both sides by the common denominator to get what is called a point slope form of the line. So usually we write it with the y's first. Y minus y1 equals m times x minus x1. So the name of the form, point slope, tells us that we should utilize this when we are given a point and we are given the slope. So if I have a point and a slope, I should easily be able to figure out the equation on my line. Kind of looking at this review, so we're kind of hustling a little here. So just a reminder, your equation is going to be y minus y1. I don't know why they put a little dot there. X minus x1. So don't forget that m. So example 5, we want to find the equation of a line that passes through 4, -3 with a slope of 5, and we want to write equation in point slope form. So this here, these are known points, so they represent my x1, y1. And then we know this is my slope, that represents my m. So all I have to do to write my equation is that I have y minus the 4 or the -3.
-3.
-3. And then my m is the 5. So then I have x minus 4. This might be able to simplify into y plus 3. We're asked to keep in point slope form, so we'll stay like this. All right, so then the next one is we are going to find an equation for a horizontal line containing the point 1, 4. So we got my x1, my y1. If I got a horizontal line, what do I know about the slope? It's horizontal. So it's like this, right? Is that an infinite slope or no slope? So when we have horizontal lines, that means my m is 0. So what they're hinting at is that now I can say I have y minus 4 equals m is 0, x minus 1. So we end up with y minus 4 equals 0, or we can say y equals 4. Okay, like I said, I know this is kind of going quickly trying to get through this part here. Do you guys have any questions? I'm worried about how fast paced this will be. Okay, at least try to get us through this first page here because it looks like we have what? 15 minutes? Okay, 16. Okay, so if we're given 2 points, so I'm going to find the equation of the line that passes the point -2, 1 and 7, 4. If I want to write an equation for this line, I need to have my slope to use point slope form. So how do I find my slope? Okay, so do I put like 7 minus -2 on top? Are you sure? Y is always on top, okay. So I need to put 1 minus 4 on top. So if you use this one, what has to go under it?
2.
2, -2. And what goes under the 4? So we get a slope of 1/3. So we actually have 2 different equations I can get here. They're equivalent. But I can have one where I have y minus 1 equals 1/3 x minus 2, so x plus 2. Or I can have y minus 4 equals 1/3 x minus 7. Wait a second, I got somebody's panicking about something. There we go. Okay, so we're saying those are equivalent equations. If we had solved those for y, we should end up with the same equation. Okay, so example 3, using the point slope form. Okay, so what we're trying to do here is they just want us to find how to write slope intercept form, which I think everybody knows. So I'm going to skip right here. The slope intercept form. So B represents a point that is 0B, your y-intercept. And M is still slope like always. And this one is y equals mx plus b. So this is slope intercept form because if we have a slope and an intercept, we can easily get it. Also, it makes it easy to graph from. Goodness, you're still got perpendicular lines. So the equation for a line that was expressed in point slope form, we're gonna solve the point slope formula in part B so that we can get a slope intercept form. So the question that we had before, just a second, let me go back and find it. In number 7, like I said, I had 2 different equations, making them both down. We had that we can have y minus 1, sorry, I was trying to find it again, 1/3 x plus 2 was one equation. And then we had y minus 4, 1/3 x minus 7, yes. So frequently we like point slope form because it easily gives us an equation. We like slope intercept form because it makes things clear what the situation is if we talk about it in terms of application problems, and it helps us graph them. So frequently the way we go about this nowadays is we do slope point slope form first, then solve for y. So we're going to solve this for y. Get my blue back. We get 1/3 x plus 2/3. So y would be 1/3 x. If I add 1, what is 2/3 plus 1? So 1 would be 3/3, right? So we get y equals 1/3 x plus 5/3. Okay, I was telling my previous class, it's like, you might know how to do the math, but then when you're given some sort of arithmetic problem, it's all of a sudden your brain kind of shuts down on you. It's like, if you just give me a bunch of variables, I'll know exactly what I'm doing. All right, so if I do this one, I distribute the 1/3, I have 1/3 x minus 7/3. And if I add 4, so if I add that 4, that would be 12/3. So 12 minus 7 would be 5/3. Yeah, but I have a minus, this start out minus, right? Like I said, when you do point slope form, if you're given 2 different points, you can end up with 2 equivalent equations. They're just not going to look the same. But if you solve them for your slope intercept form, you're going to get the same equation. So just a reminder, equivalent doesn't mean the same. Equivalent means it has the same set of solutions. See how much time do I have here? Can I do this next part? I confused myself because I was on the other page for my equation. We want to write an equation x plus 2y equals 8 in slope intercept form. So when you say slope intercept form, that's always essentially the same thing as solve for y. All right, divide both sides by 2. We end up with y is equal to 4 minus 1/2 x. But if you like it to be mx plus b, I can always rewrite it as negative 1/2 x plus 4. All right, so what's my slope?
-1/2.
Negative 1/2. What is my y-intercept? 4. You can say 4, or sometimes you'll see an ordered pair 4, 0. But we know we get this point here. Okay, so do I go like this for my slope? I go down? And I completely missed my line. I'm going to stop there because I'm going to get attendance for everybody that got finally. Let me bring that back up again, sorry. I didn't know somebody was still writing there. So here we got y is negative 1/2 x plus 4. Slope is negative 1/2. we said that B or Y intercept is going to be 4, or we have an ordered pair, 4, 0. So our line was this. Oh, that was a violent sneeze somebody had out there.